Hello viewers, welcome to CEC Gurukul lectures. In my previous lecture, I had discussed with you the mechanism of SN1, that is unimolecular nucleophilic substitution reaction. In today's lecture, we shall be discussing the effect of factors on the rate determining step. We know that SN1 reaction takes place in two steps. The first step is the rate determining step, in which the alkyl halide ionizes to form a carbocation and an anion. It is the second step, which is the fast step, in which nucleophile reacts with the carbocation to give the product. Hence, in rate determining step, it is the substrate which ionizes to give the carbocation and an halide anion. That means the structure of the substrate, the nature of the carbocation being formed, and the leaving ability of the halide anion, which will affect the rate of the reaction. Solvent also plays an important role in deciding the rate of the reaction. As you know that the rate limiting step of the SN1 reaction is the ionization of alkyl halide to form a carbocation. This reaction is highly endothermic. Consequently, the rate of SN1 reactions depend strongly on the carbocation stability. According to Hammond postulate, the activation energy of the rate determining first step will be inversely proportional to the stability of carbocation intermediate. That is, the more stable the carbocation, the lower activation energy, and hence faster the rate of reaction. Therefore, carbocation stability is a primary consideration in SN1 reactions. We know that the energy of activation for formation of methyl carbocation is highest, and it is least for formation of tertiary carbocations. In general, we can say that more substituted carbocations are more stable. The alkyl groups stabilize carbocations by donating electrons through sigma bonds, that is, through inductive effect, and through overlap of filled orbitals with the empty p orbitals of carbocation due to hyperconjugative effect. As you can see on your slides, I have shown the structure of tertiary butyl carbocation, which is being stabilized due to inductive effect. The carbon having the positive charge is attached to three methyl groups. These three methyl groups exert a plus I effect, and due to the cumulative effect, plus I effect of these three alkyl groups, the positive charge on carbon is neutralized to some extent. Secondly, if we look into the hyperconjugative structure of ethyl carbocation, then we find that there is weak overlap between the vacant p orbital and the sigma bond at alpha position, that is alpha and the hydrogen, that is the sigma bond between the carbon, alpha carbon and alpha hydrogen. And due to this overlap, the carbocation is stabilized. That means more the number of alpha hydrogens, more will be the stability of the carbocation due to hyperconjugative effect. That means tertiary butyl carbocation is most stable since it has 9 alpha hydrogens. Now the question arises, what are alpha hydrogens? Alpha hydrogens are those hydrogens which are attached to alpha carbon. And alpha carbon is the carbon which is next to carbon bearing the positive charge. So tertiary butyl carbocation has 9 alpha hydrogens, followed by isopropyl carbocation which has 6 alpha hydrogens, followed by ethyl carbocation which has 3 alpha hydrogens, and methyl carbocation is least stable since it is not attached to any other alkyl group. Therefore, the question of the stabilization by inductive or hyperconjugative effect does not arise. Carbocations can also be stabilized by rearrangements through 1,2-hydride or 1,2-methyl shifts. For example, if we consider propyl carbocation, then through 1,2-hydride shift, it will convert into isopropyl carbocation, which is more stable than the primary carbocation, which is propyl carbocation. These reactions we will be discussing in great details in subsequent lectures. That means, on the basis of stability of carbocation intermediate formed, we can say the order of reactivity of alkyl halides is tertiary alkyl halide, more reactive than secondary alkyl halide, which in turn is more reactive than primary alkyl halide. Among primary alkyl halides, methyl halide is least reactive. Now let us look at some other organic halides. For example, benzylic and allylic halides. Primary benzylic and allylic halides readily undergo SN1 reactions as their carbocations are stabilized by resonance effect. For example, allyl bromide is a primary halide. Nevertheless, it undergoes SN1 reaction at the same rate as which the secondary halide undergoes. The reason being, the allyl carbocation formed is resonance stabilized with the positive charge spread equally over 2 carbon atoms. As you can see, allyl bromide ionizes to give an allyl carbocation, which is stabilized due to interaction between the pi electrons and the positive charge on carbon, as a result of which we get a second resonating structure or the contributing structures. In this case, both the contributing structures are equivalent, that is, they are mirror images of each other. So we will get only one product. When this allyl carbocation reacts with water, which in this case will act as a nucleophile as well as solvent, we get only one product, which is allyl alcohol. Since the reaction is brought about by water, that is, it is breaking the bond between the carbon and the bromine atom. Here it is acting as a solvent. So this reaction is also known as solvolysis. Let us take a second example of allylic carbocation. If the allylic carbocation intermediate has different alkyl groups bonded to their sp2 carbons, then 2 different products will be formed. Reason being, the 2 allyl carbocations formed, the 2 resonating forms of allyl carbocation formed are not equivalent. As you can see, on ionization, 1-bromo-but2-ene gives a primary carbocation, which on resonance gives us a secondary carbocation. So these two carbocations are not equivalent, or they are not similar. So in this reaction, two different products will be formed. When primary carbocation reacts with water, it gives us but2-ene 1-ol. That is a primary allylic alcohol. Whereas when a secondary allylic carbocation reacts with water, it gives but3-ene 2-ol. That means it is giving us a secondary alcohol. And we know secondary alcohol will be formed in higher percentage since secondary carbocation is more stable and its rate of reaction will be faster. Unlike allylic systems, there is no benzylic rearrangement, since that would result in loss of aromaticity and only one product will be formed. If we look into the example of 2-bromo-1-phenyl propane, then this ionizes to give us a secondary carbocation. And if we look into the resonating structures of this carbocation, we find they are not aromatic in nature. Therefore, they are the unreactive forms. Hence, we can say that the order of reactivity of alkyl halides will be influenced greatly by the stability of the carbocations. That is, tertiary alkyl halides and benzyl halides will be most reactive, followed by allyl halides and secondary alkyl halides, which in turn will be more reactive than primary alkyl halides. And among primary alkyl halides, methyl halides are least reactive. Let us look into other substrates. That is, if we consider aryl and vinyl halides, then aryl and vinyl halides do not undergo nucleophilic substitution reactions. The reactions may be SN1 or they may be SN2. If we take an example of SN1 reaction, then in that case, the carbon is sp2 hybridized, and this sp2 hybridized carbon is attached to a halogen. Here, resonance takes place due to interaction between the lone pair of electrons on halogen atom and the sp2 hybridized carbon, as a result of which CX has a partial double bond character. That means the bond between the carbon and halogen will be shorter and stronger. As a result, it will be difficult to break this bond. Second point, alkyl carbocations are more stable than vinyl and aryl carbocations, since in alkyl carbocations, carbon bearing the positive charge is sp2 hybridized, whereas in vinylic and arylic carbocations, this carbon is sp hybridized. And we know that the sp hybridized orbitals are more electronegative because they have less p character. They are not able to donate more electrons to the positive charge located in the p orbitals, and thus they are unstable. As you can see on your screens, the vinylic halide does not undergo bond dissociation easily, And if it undergoes, the carbocation is not formed because it is too unstable since the positive charge is on sp-hybridized carbon. Similarly, from bromobenzene, we do not get an aryl cation. Again, because the carbon bearing the positive charge and is sp2 hybridized and it is too unstable to be formed. The second factor which will affect the rate of the reaction is the leaving ability of the departing group. That is, how good the leaving group is. We know that the CX bond breaks in the rate determining step of a SN1 reaction. The SN1 reaction increases with a good leaving group. What is a good leaving group? A good leaving group departs readily, and thus the bond cleavage between carbon and the halogen atom, or we can say carbon and the leaving group, is faster. We know once the bond breaks, the carbocation is formed. That means it is the rate of carbocation formation which will decide how fast the reaction will be completed. That is, faster the carbocation is formed, the faster will be its reaction with the nucleophile, and hence faster will be the completion of the reaction. A leaving group departs with bonding pair of electrons. That is, when a bond breaks between carbon and the halogen atom, it is the halogen atom which will depart with the bonding pair of electrons. So since it is departing with the bonding pair of electrons, it is how efficiently it will hold these electrons will decide whether the departing group is stable or not. The best leaving groups are those, that means, which can stabilize the negative charge. That means they should be weak bases. And we know as we go from left to right in the periodic table, the electronegativity of the atom increases, and so does the ability to leave. That means halogens are good examples of leaving groups. But among halides, iodide is the best leaving group and fluoride the poorest one. This is because the leaving ability increases as one goes down the group. As one goes down the group, the size of the atom increases, and it is able to delocalize or disperse the negative charge more efficiently. The second point that we have to take into consideration is that iodide is a weak conjugate base of a strong acid, that is hydroiodic acid, whereas fluoride is a strong, that is, it is a poor leaving group or a poor base of a weak acid, which is HF. Hence, among halides, iodide is the best leaving group, followed by bromide, followed by chloride, and followed by fluoride. That means alkyl iodides will be most reactive and alkyl fluorides will be least reactive towards SN1 reaction. This order we observe even for SN2 reactions. Now let us consider the given two reactions where the reaction conditions are same except the leaving group. The first reaction is significantly faster than the other because in the first reaction the leaving group is an excellent leaving group. Now the third effect, which will strongly affect the rate of reaction, is the solvent. We know that the first step in this reaction, the SN1 reaction, is the ionization of the substrate to form the ions. So, to facilitate the charge separation of the ionization reaction, in the rate determining step, a good ionizing solvent is needed. In other words, the solvent should have high polarity and solvating power. The dielectric constant is a measure of polarity of solvent molecules and their ability to orient themselves between ions. This reduces the electrostatic forces which one ion exerts on the other. The higher the dielectric constant, the more polar the substance and faster will be the rate of the reaction. Solvents whose dielectric solvent is 15 or less than it are non-polar in nature. SN1 reactions occur more readily in polar protic solvents that stabilize ions rather than in polar aprotic solvents. A polar protic solvent like water will largely increase the rate of ionization since it can solvate the carbocation and the anion. Polar protic solvents such as water and methanol have a permanent dipole. Now, how do these solvents stabilize the ions? If we consider water as an example, then the partial negative charge on oxygen will have a dipole ion interaction with the positive charge on carbocation and thus decrease the energy of the carbocation and hence stabilize it. On your screens, you can see the solvation effect of water molecule. In this, the lone pair of electrons on oxygen interact with the positive charge on carbon through ion-dipole interaction, thus stabilizing the carbocation. The water molecule forms a cage round the carbocation, stabilizing it. Since the hydrogen atom in water is highly positively charged, it can interact with the halide anion and stabilize it. The hydrogen atom is highly positively charged since it is attached to an electronegative oxygen. And here you can see on your screens that the halide anion is being stabilized due to ion-dipole interactions between the halide anion and the hydrogen of the water molecule. Polar protic solvents not only stabilize the carbocation, they also stabilize the transition state, because in transition state, the charge character or the ionic character is more, since here the leaving group is departing with the bonding pair of electrons. Therefore, they stabilize the transition state more as compared to the reactants. On your screens again you can see that tertiary alkyl chloride ion in the transition state is being stabilized by solvent molecules, that is water molecules. In this case, the charge separation between the carbon and halogen is great, because here the chlorine is departing with the bonding pair of electrons, as a result of which there is bond stretching and more positive charge is developed on the carbon, and halogen has more negative charge as compared to the reactant. the positive charge on carbon is being stabilized by the lone pair of electrons on oxygen, and the negative charge on chlorine is being stabilized by the hydrogen, that is through hydrogen bonding here. This facilitates in the ionization of the transition state, which gives us carbocation and an halide, that is chloride ion. These are again stabilized by the solvent, that is water molecule. That means that the rate of SN1 reaction depends on the polarity of the solvent. In more polar solvents, reaction rate is more. That means if we take two polar solvents, that is water and methanol, and compare their rate of reaction, then we find that the rate of reaction will be higher in water, whose dielectric constant is 81, as compared to methanol, whose dielectric constant is 33. I have depicted this reaction on your screens, in which the substrate is the same, which is reacting with the same nucleophile, that is cyanide, to give us the same products. The only difference is the solvent. In one reaction, we've taken water as the solvent. In the other reaction, we've taken methanol as the solvent. And what we find, the reaction in which we have taken water as the solvent, there the relative rate of reaction is 150,000 times greater than the reaction which is being carried out in methanol. So now if we look into the energy graph of the reaction, in which we are seeing how the reaction progresses and what is the change in energy during the progress of reaction. In this case, we have taken two different solvents and we are seeing the effect of the solvents on the rate of the reaction. With the red line, we have depicted non-polar solvent, that is the rate of reaction and the energy change, whereas the green line or the green graph is indicating the progress of reaction and the changes energies in the polar solvent. And what we find, when the reaction is conducted in the polar solvent, the energy of activation is less. The energy of activation is less since the transition state as well as the ions formed as the result of the ionization are stabilized by the solvent. This stabilization effect is not possible in non-polar solvents. Now if we look into the effect of nucleophile on the rate of the reaction, then we know that the nucleophile does not participate in the rate determining step of the reaction. Hence, the reactivity of nucleophile has no effect on the rate of reaction. So we can summarize today's lecture by saying that it is the structure of the substrate which will affect the rate of the reaction, that is benzylic, tertiary alkyl halides are more reactive as compared to allylic and secondary alkyl halides, which in turn are more reactive than primary alkyl halides. And methyl halides are least reactive among primary alkyl halides, whereas aryl halides and vinyl halides do not undergo nucleophilic substitution reactions. The better leaving group, that is, which is a weak base, is an excellent leaving group. That means if we compare only the leaving ability of halogen atoms, then iodide is the best leaving group and fluoride is the worst leaving group. In fact, alkyl fluorides do not undergo nucleophilic substitution reactions. And now if we look into the solvent effect, then we find that it is the polar protic solvents which increase the rate of reaction because they are able to solvate the cations and anions more effectively. They stabilize the transition state, leading to the intermediate carbocation and halide ions more than they do the reactants, and they lower the activation energy, hence the rate of reaction is fast. Since the nucleophiles do not take part in the rate determining step, they do not affect the rate of the reaction. Thank you.